Hello everyone, welcome back to the chat. In this video lecture we shall solve this problem, minimum path sum. In this problem we are given a matrix of dimensions m cross n or a grid of dimensions m cross n. It is filled with non-negative numbers, that means it has positive numbers and it may have 0 inside it. We have to find a path from top left corner to the bottom right corner which minimizes the sum of all numbers along its path. That means the sum of the numbers along the path should be minimized, and we can make two moves. Either we can move right or we can move down. Okay, so let's see an example. So in this example we're given a grid of dimensions 3 cross 3 and the optimal path, the path with the minimum sum, starts from 1 3 1 1 1 and the sum is 7. That means the cost is 7. And there is no other path which gives me cost less than 7. Okay, so this is the answer for this given grid. Let's see the constraints of the problem. The dimensions of the grid goes up to 200. That means at max we can have a matrix of dimensions 200 cross 200, and the numbers in the grid goes up to 100. Okay, so let's see how we can build the solution for this problem. So this is a grid of 3 cross 3. Okay, and we want to find the number of paths to move from top left to bottom right, and there are two directions that we can move here, right and down. Okay, so let's count the number of paths, the possible paths that we can make. The first path is straightforward, just move down and then move right. Okay, the sum is 1 plus 1 2 plus 4 6 plus 2 8 plus 1 9. So this is one of the paths. Another path is this, move straight to the right and then move down. 1 plus 3 4 plus 1 5 plus 1 6 plus 1 7. Okay, another way is just move down and then move here. Okay, so 1 plus 1 plus 5, that is 7 plus 1 8 plus 1 9. Okay, so let's see another path, that is move right and then move down, right down. Sum is 1 plus 3 4 plus 5 9 plus 1 10 plus 1 11. So that would give me 11. Another path is move down, move right and then move down. 1 plus 1 2 plus 5 7 plus 1 8 plus 1 9. Move left, move right, move down and then move right. 1 plus 3 4 plus 5 9 plus 2 11 plus 1 12. Okay, so these are the possible paths that we can have. Fine. So which one is giving me the least value, least cost? This path, the path in which I am moving right and then I am moving down. So along this path I am getting the value 7. Okay, so how would I know? Let's see how many paths in a matrix of dimensions n cross m are there. Well, we know that to reach this cell I have to start from this cell, and the right moves are m minus 1, while the moves downwards are n minus 1. The total number of moves in any path will be m minus 1 plus n minus 1. So irrespective of the path that we take, the number of moves will always be this. So it will give me m plus n minus 2. Okay, so out of these moves, how many ways are there to select m minus 1 downward moves? These are the number of ways to select downward moves. Okay, so I'm using the simple formula NCR, that is number of ways to select R items out of N items. Okay, so I want to select M minus 1 steps out of total steps, which are M plus N minus 2, that is M plus N minus 2 C M minus 1, which is also equals to, which we can say which is also equal to the number of ways to select rightward moves, the moves towards right, that is N minus 1. Okay, so for this matrix where N is equals to M, that is 3, the answer to this, the number of paths would be 3 plus 3, 6 minus 2, 4, 4 C M minus 1, that is 2, which would give me 4 factorial divided by 2 factorial into 2 factorial, and this is going to give me 6. Okay, so there would be 6 paths by which I can reach this cell starting from this cell, and that is indeed the answer. Here we have 6 paths here. Fine, and out of all these paths, this path is giving me the least value, least cost, and hence the answer for this exemplar test case is 7. Okay, so let's see how we can build the solution for this problem. So imagine this grid in which we want to find the minimum cost path to land at this cell. Okay, so to land at this cell, I either come from this cell or from this cell. Fine, that means if I want to find the minimum cost path to land, let's call it to reach this cell, that is 2 and 2, I need to know the minimum cost path at this location and at this location. Why? Because let's say the minimum cost path to reach this cell is X and the minimum cost path to reach this cell is Y. So the answer that the minimum cost path to reach this cell would be minimum of X and Y plus the value present at this cell. That means min of X and Y plus the value at that position here, 1. Okay, because since I'm landing here, I have to add this value. Fine, and there is only one way to reach. There are only 2 ways to reach this cell. That is either come from this cell or this cell. So that's giving me a recurrence relationship. That means for any generic cell I and j, if I want to reach this cell starting from the first cell, such that the path that I am taking has least cost, it has least cost, then I have to check for minimum of the cost for cells I minus 1j and ij minus 1. Okay, that's all. So that's giving me a recurrence relationship that I am going to show you. So this is the recurrence relationship that would be used to find the minimum path sum. So here you can see that to reach a cell I and j, I am coming from either I minus 1j from the cell which is above this cell. So to reach cell this, I am either coming from the cell which is above it or from the cell which is left to it. Okay, so I'm computing starting from, this is the starting cell, to reach this cell. So let's say it is X, and then the min path sum to reach this cell, that is Y. So this function gives me the minimum path sum to reach cell ing. Okay, so and after taking the minimum of these two results, I will add the value that is present at that location ing, because I am landing at this cell. Fine. So that's the recurrence relationship. Let's see how we can implement this in code. So this is the implementation. Before that, let's understand the base case. In the base case, we can see that we have the base case is the case when we are standing at this position. So we are standing at the starting location. So this one. So I'm standing here. Okay, and this is the base case, because to reach this cell, all I require is the value at this cell. Fine, because because here I do not have any other cells, so I'm starting from here. The min path cost here has cost of 1. So if I'm standing at first cell, then I simply return the value that is present at that cell. Here you can see that. Fine, standing at first cell, return the value at the present at that cell. Otherwise, if I am out of the boundary, so I am out of the boundary either here or here, in that case I'm returning a number which is very large. Why? Because it takes, let's say, infinite cost to reach some cell inside this boundary from some hypothetical cell which is outside this boundary, which is not there. That's why I have to return some infinite. But since infinite is a no number, there is no number like infinite, so we return a very large number. How much large number we have to return? It depends upon the path which has the largest cost. So in this matrix, find the path which has largest cost, and this number would be just greater than that cost. So it would work for the number just greater than that cost will work, and that's why I'm taking a very large number which is beyond the possible path sum which can be obtained from this matrix. Okay, because 1 is to the power, it is 10 is to the power 9, while the numbers in this matrix goes up to 100 only. Okay, so these are the base cases. Let's see the recurrence relationship. So this is a recurrence relationship. I am recurring for the cell just above it and for the cell just left to it, and taking the minimum value here and returning the minimum of these two values. Fine. That's how the recursive code is working, and let's analyze the time and space complexity for this code. Okay, so let's see the time complexity for this code. You can see that initially the function is called at this cell, and there are two ways to reach this cell, that is from this cell and this cell, and hence we are reducing either a row in first case, that we are reducing a column. So we are moving up or we are moving to left, and we are taking minimum of these two results and then adding the value which is present at this location. Okay, that is plus, so min of these two plus grid 2 2. Okay, so this will be added to the minimum of the results of which are returned by this function and this function. Okay, now we see that the branching factor for each function is 2, and the height of this tree goes up to max of n m, where n and m are dimensions of the given matrix. Fine, because we can see that we can observe this branch 2 becomes 1, then it becomes 0. Okay, so if it would have been, let's say, 5, then here we would have another function call. So rather than this -1, I would have, let's say, 5 4 3 2 1 and so on. So that's why I'm taking the height as max of n into m. So the time complexity would be 2 raised to the power this max of n cross m, n comma m. So this is the time complexity, and for the constraints, like the dimensions goes up to 200, and 2 raised to the power 200, 2 raised to the power 200 is a huge number, and this will give me TLE, and it will not be executed within 1 second. Therefore I have to improve upon it, and let's see how we can do that. So to see that, to improve upon a recursive code, we have dynamic programming. If the code that we have satisfies two properties of dynamic programming, the first one is optimal substructure and second one is overlapping subproblems. So you can see that here for this MP11, that is min path sum 11, I'm calling this function again and again at these indices. Here you can see that means I am computing the results for a particular pair of indices more than once, and that is a redundant computation, and this is what we call as overlapping subproblem. Okay, so and also we are building the solution of a larger problem from the solutions of a smaller problem. Hence it satisfies the properties of dynamic programming, so we can memoize the results which are computed here. So once the result for this function is computed, I can memoize it such that it can be used when this function has to be called again. For instance, once I have the result for this function, let's say x, stored somewhere, and I call this function, I try to call this function again, I do not have to make the computations again, rather I simply return x. Okay, right from here. So that's the idea. Let's see how we can implement memoization. So you can see that in the memoization we are using a DP table of dimensions n cross m, where n are the number of rows and m are the number of columns, and we see that we initialize the DP table with -1 so that we can check that whether for a particular I and j pair the results are computed or not. If they are computed, then -1 wouldn't be there, otherwise we would have -1 as a default value, so that we can check whether the results are computed or not. Okay, so let's see how the code has been improved. You can see that the base cases stays the same. Here you can see this is the case of memoization. We have memoized the results for the pair ij. Okay, we have memoized the results for this pair, and since it says that if dpij is not -1, that means the result for this pair has been computed, and hence we return the result right from here. Otherwise we recur for the column just above it and for the column just left to it, and we take minimum of these two. Okay, and we store that for that particular pair of indices, so we store that here. Okay, so that's how we have improved the time complexity. Let's first see that what is the time complexity for this code. So you can see that once the result for a particular I and j pair has been computed, we would not call the same function for this pair. Okay, that means all we have to do is to, if we want to count the number of function calls like we did in this recursion tree, we just have to count the number of unique I and j pairs. Okay, so unique pairs means, okay, so if I goes from 1 to n and j goes from 1 to m, then you can see that the number of such unique pairs would be n cross m, and that would be the number of function calls as well. Hence the time complexity would be n cross m. And what about the space complexity? Since we are using a DP array of dimensions n cross m, the space complexity will also be n cross m. Fine. Has it improved the complexity of the code, the running time of the code? Yes. In the previous case, the complexity was exponential, 2 raised to the power n. In this case, it has become quite, for dimensions of order, let's say 100, it will work in 100 cross 100, that is 10 raised to the power 4, which will work fine within the time limit, that is 1 second. Okay. So that's how we have improved the time complexity of the solution, but at the cost of space. So we're using extra space, but the time complexity has indeed improved. Okay, so we know that this is the memoization approach of solving a dynamic programming problem, but there is another approach to solve a DP problem, that is bottom-up manner. So in bottom-up approach, what we do, we know the solutions of smaller problems and we use those solutions to build the solution for a larger problem. Okay, so let's see how we do that. In this approach, we use two pointers. The first pointer goes from I to n, that is, it iterates over all rows of the matrix, and for each row, we iterate over all columns of the matrix using pointer j. Okay, and this is the base case that we are handling. That means if we are at the first row or first column, then we simply if we are at first row and first column, then we simply put the value at that location which is present in the grid. Otherwise, we have two cases. That means if dpij represents the minimum cost to reach the column ij from 0 0 from the first column, then I would like to know the minimum of min cost path of the cell which is just above it, that is I minus 1. So this location has stores the min cost for the path from 0 0 to I minus 1 to j, and for the min cost of the column to the left of it, that is dpi j minus 1, plus the value at the location that we have here, grid ij, and that's how we compute the result for a particular column I and j. Okay, so this is how we are handling here. We are computing the result. We know this result. So from this result, that is the minimum cost to reach the cell which is just above the current cell I and j, and the minimum cost to reach the cell which is just left to the current cell, and we take the minimum of these two and we store it at the location that we are currently standing on, that is dpij, and we return the answer finally, which is present at the last cell of the matrix. This is how we solve the problem in bottom-up manner. The time complexity stays the same, n cross m, while the space complexity is also n cross m, because we are using the same matrix, and the number of pairs that we are iterating, you can see I goes from 1 to I iterates for n times, j iterates for m times. Hence, we would have n cross m time complexity. Okay, so that's all for this video. Let me show you the code implementation for the approach that I have explained here. Okay, so this is the code implementation of the problem that I explained in C++ language. Here is the base cases, and this is the memoization case. This is the recursive conditions where I am recurring for the cell just above it and the cell left to the correct cell. Finally, I'm storing the result for that particular location, and I'm returning the result right from here. And this is the implementation in Java, and this is the implementation in Python. Thank you so much for your patience. Stay tuned for more such videos, and do not forget to like, share and subscribe.